There's a reason that our bodies are about 56 to 60% water, that the earth is mainly water. Obviously, even in bones, we have water. So obviously, for this much on this earth to be water, there must be some very good properties of water. And that's what this discussion is on. Basically, the good properties of water are based upon two things we've already discussed: the bonding patterns. The intramolecular bond in water that holds one water molecule together, go back and study it, is a polar covalent molecule. That's number one. The bonds that hold water molecules together, which makes it stick together, are hydrogen bonds. They give what we call the intermolecular bonds. So everything is based off of that. Here's some properties of water. Water is a good solvent. It participates in biochemical reaction, absorbs and releases heat very slowly, requires a large amount of heat to change from a liquid to a gas, has a cohesive nature, will stick together, exerts a surface tension, and serves as a good lubricant. Let's examine those very quickly. Water is a good solvent. It's not the universal solvent, because then what would contain it? But it does dissolve a lot of stuff. Now, what's the major thing? Water dissolves atoms or molecules that show an exposed charge. So for water to dissolve something, it must show a charge. That's why fats don't dissolve in water, because they don't expose a charge. They float at the top. Why is this? The reason is that water itself is charged, and you know charges attract charges. The reason it's charged is because the molecule is polar covalent. Study your old material. What does water like to dissolve best? First thing it likes to dissolve best are individual ions. Remember, study back. An ion is a charged atom as a result of a gain or loss of electrons, like your sodium and your chloride and so forth. Because water is charged, it will dissolve those. Now that's if it's in the atom form. If it's in the molecule form, it likes to dissolve ionically bonded molecules. Go back and study the PowerPoints and the text. An ionically bonded substance has a full and complete separation in charge because the more highly electronegative atom literally drew the electron or electrons from the other one. So one side is fully charged. Both sides are actually fully charged. One side is charged positive and the other side is charged negative. So if we say, what does water like to dissolve on the molecular, it would be ionically bonded. What will water dissolve after that? Something that is polar covalent like itself. The more polar covalent it is, that means the more polarity, the better it likes it. And I mentioned, but I didn't get into it, that something called the dipole moment will determine the degree of polarity of that. What will water not dissolve? Something that does not show a separation or charge, like your oils and your fats. Okay. Here's an example showing sodium chloride being surrounded by water. And you can look at that in my PowerPoints. Another demonstration. Water participates in biochemical reactions. Now, our biochemical side will come up in organic chemistry, which will be the next PowerPoint series. But what happens is that water, if you look at this, and we'll look at it again, when it comes to biochemicals, then water can be pulled out and form bonds. So we call that a dehydration synthesis. Water is being pulled out. You'll see it better when we do the organic. If I want to split organic molecules apart, we introduce water, and that splits them apart. So to put them together would be this. This would be an example of, go back to your notes, anabolism. This right here would be an example of catabolism, splitting them apart. So go over and over your notes. Water absorbs and releases heat very slowly. Okay, let's go back very quick. Heat, we've said, was the total kinetic motion of particles in an entity. We said we could measure heat by using temperature, which was the average. In order to increase the kinetic energy in something, the molecules must flow independently. They must flow independently. But however, in water, remember, bonds between water molecules, hydrogen bonds, hold it together. So virtually what has to happen is heat would have to come in quite a bit to be able to virtually break those bonds between the water molecules. Takes a lot to do that. So if we go back something else, that means water has a high specific heat. By virtue, water has a high specific heat, and by virtue of the fact, studying back, that a calorie is using water as its basis, then a calorie packs a lot of energy, we can say. A lot of heat. So when we look at that, that's the reason that areas close to water don't fluctuate in temperature as much. Look here how these temperatures are more mild than if we go back here. So water can gain a lot of heat without changing the temperature. And it also can lose a lot. So study that. I think it's pretty much self-explanatory. In order to increase the temperature, as I alluded to, you must break the bonds. And you can look at that on your own. Here again are the intermolecular bonds. Now, when we look at how many intermolecular bonds we have, you could go to this right here to see how many bonds, hydrogen bonds, would be. So if I take a glass of water, which is 8 ounces, you can see that that's about 227.3 grams. If I wanted to figure out how many moles, one mole of water is 18 grams. Go back to your material. Each mole has 6.02 times 10 to the 23rd. And each molecule of water is being hooked by 2 hydrogen bonds. So you quickly can see, I'll say it like this, that there's a lot of hydrogen bonding in water, which then a lot of stuff has to be broken on those bonds in order to increase the temperature, even though hydrogen bonds are only 1/20 of the strength of covalent. Okay? So this is the explanation on that right here. As you can see, water has a large amount of heat to change from a liquid to a gas. That piggybacks on the other because in the centigrade scale, Celsius, you have to reach 100. And if it takes a lot of heat to go from each degree, so if you started, let's say, at 50 degrees for water, centigrade, it would take a lot of heat to go to 51, and then 52, and then 53 before you got to 100. Water has a cohesive nature. That means water will bond to water. That's how you can draw it up on a straw. What is that due to? That's due to the hydrogen bonds. This cohesive nature also gives water a surface tension. When you look at a bead of water on the table, look how tight the surface is. Look how tight the surface is. This cohesive nature also assists in plants being able to draw water up through them, that cohesive nature. This surface tension is an expression of the intermolecular bonds between the water to make it tight at the surface, very tight at the surface. See right here, that would be a droplet of water right there. How tight these bonds are gives a surface tension there. So much so that this insect here can literally walk on it. Water serves as a good lubricant. It's not as good, I would say, as WD-40, but it is a good lubricant. The reason has to do with, first of all, if you're going to float something on the water, you have to first look at that water exerts a surface tension, a tight surface. Okay. So it's not going to smash down as easy. Then when you come to the fact of the density of water, anything it floats must have less density than the water itself. So when we look at this aspect, we talk about the flotation, this density. But the other aspect is, why is a tight surface of the water not the same as a tight surface of a table where you would slide across? That has to do with this factor very quickly. As you should know, that a glass of water does not have the same temperature from the bottom to the top. The top of the glass of water, the top surface, is almost in the vapor stage, because remember, water can spontaneously evaporate. So that very top layer of water is almost in a vapor state, unlike it would be on a table. So essentially what's ever floating over the water is floating over a layer of vapor. So by virtue of the water having a nice density, by it having a surface tension, by the uniform nature of the water in temperature and not being the same from bottom to top, with the top being more vaporized, that can explain why it acts as a good lubricant. Okay? Now, when we get to the surface tension, and in ANP2, because we have water in our body, and particularly in our lungs, as we exhale, little air sacs in the lungs would get smaller and would attempt to collapse the lungs, because in these little layers of water on the air sacs, as you would exhale, the little sacs would collapse because water on one side of the sac would see the other side and pull it in by the cohesive nature. Then you wouldn't be able to breathe. So what we'll talk about in ANP2 is something to prevent, to break up this surface tension called surfactant. Very important concept. Remember, ANP1 is to set the stage to understand ANP2 and the rest of ANP1. So these first few chapters are to kind of set the stage in science to understand the rest of the book. All right. Thank you very much there.